Alright, so in this video I'm gonna be explaining another important paper with the title When Do GNNs Work? Understanding and Improving Neighborhood Aggregation. This HK paper in 2020. Graph neural networks have been shown to be powerful in a wide range of graph-related tasks. While there exist various GNN models, a critical common ingredient is neighborhood aggregation, where the embedding of each node is updated by referring to the embedding of its neighbor. This paper aims to provide a better understanding of this mechanism by asking the following question: is neighborhood aggregation always necessary and beneficial? In short, the answer is no. We carve out two conditions under which neighborhood aggregation is not helpful. First, when a node neighbors are highly dissimilar. When a node's embedding is already similar to that of its neighbors. We propose novel metrics that quantitatively measure these two circumstances and integrate them into an adaptive layer module. So this simple graph convolution is just a simple formulation of a graph convolution network. Neighborhood aggregation takes advantage of homophily effect in networks, which states that connected nodes should be similar. Taking this one step further, the neighbors of a node should be similar among themselves. When the neighbors disagree, we take this as a warning that the assumption may not hold and the aggregated information may be noise. To measure the diversity of a particular node neighborhood, we compute the entropy among neighbors. When X is a feature space, F is the probability density function of features of nodes to use neighbors. However, since this PDF is a sum of Dirac functions at each neighbor over high dimensional space, computing this differential entropy is infeasible and is also not very informative. Alternatively, we use the predicted labels to calculate the label distribution of nodes to use neighbors and calculate its discrete entropy. Towards the other end of the spectrum, neighborhood aggregation may be redundant when a node features are sufficiently similar to its neighbors. For example, the label of node 25 is already the same as all of neighbors when L is equal to 1, so the aggregation will not change its label and is unnecessary. We characterize this similarity by calculating this pointwise mutual information between center node U and its neighbor N of U. Since we do not have prior knowledge of the probability distribution of neighbors' features, we assume it follows uniform distribution, which makes P a constant. So we can calculate the score of node U like this. U is the center node. And this neighbors of U is a set of neighbors of U, and F sub U is a node feature of U. Similarly, we can use the one-hot predicted label to calculate the metric. If this score is larger, node U is more similar to its neighbors. So now this Z here is a random variable that controlling the usage of neighborhood aggregation. Our update function resembles a residual. So the gate is computed from score sim and SCORM ETP. So the activation sigma squeezes the value from z to this interval. When either of the scores is large, z takes on a small value close to 0. Norm is the batch normalization operation to rescale the scores so that they are comparable across layers. For simplicity, we use one hot predicted label to calculate the score, and since we do not have prior knowledge of the actual class size in practice, we assume all the label classes have the same size. So the label class size term is a constant and is left out from calculation. To compare with the attention-based models, we can extend our base model to handle attention weights over neighbors. We can also extend our metric to multi-head attention, like this. So they did experiments on Cora dataset, CiteSeer, PubMed, and these are their results. When they compare their model with, for example, GCN, you see some improvement on all datasets. Also, they did node classification performance under 20 labeled data per class setting. So they compared DeepWalk with their method or GraphSage. You see some improvement.